Recall that when we spoke about objects undergoing translational motion, we said that we can describe objects undergoing translational motion by using certain physical quantities known as translational or linear motion quantities. And some examples are listed above. So we have average velocity and instantaneous velocity, as well as average acceleration and instantaneous linear acceleration. Now, we begin our discussion on angular and rotational motion. So this is a different type of motion than translational motion, and that means we're going to deal with different but analogous quantities known as angular or rotational quantities. So let's suppose we have the following object that is a two-dimensional object, and the object is rotating in the counterclockwise direction. Now this point is our axis of rotation. Now whenever the object rotates in the counterclockwise direction, the object is said to rotate in the positive direction. When the object rotates in the negative direction, that is said to rotate in the clockwise direction. So let's suppose our object is rotating in the positive direction, and we choose a point, and the point rotates from point 1 to point 2. So we begin at this point, our object rotates over some time interval and ends up at point 2. Now when the object is at point 1, the radius of the circle makes an angle theta 1 with respect to some reference axis, this blue axis. And when the object is at point 2, the angle now is given by theta 2. Notice the angle increased. And that's exactly why we say when the object rotates in the counterclockwise direction, the direction is positive because the angle that this point makes increases. So, in the same way that we spoke about average velocity and instantaneous velocity, we can talk about average angular velocity and instantaneous angular velocity given by the Greek symbol lowercase omega. So this bar simply means we're talking about the average. And in the same way that the average linear or translational velocity was the change in our distance or displacement divided by change in time, our average angular velocity is also the difference between our two angles. So theta 2 minus theta 1 divided by t2 minus t1. So the formula for average angular velocity is given by this equation. Simply take the ratio of change in our angle and divide it by change in time. Now, in the same way that instantaneous velocity was the derivative of our displacement function with respect to time, our instantaneous or simply angular velocity is derivative of our theta function with respect to time, our angle function with respect to time. So we're taking the limit of the ratio as our change in time approaches 0. Now we can also talk about average and instantaneous angular acceleration. And this is given by the Greek symbol alpha. Once again, the bar simply means we're talking about average. So if we look up here at translational motion quantities, we see that average linear acceleration is given by taking our change in velocity and dividing it by change in time. In the same way, we get our average angular acceleration by taking our change in angular velocity and dividing it by change in time. And to get our instantaneous or simply angular acceleration, we take our derivative of the angular acceleration function, or we take the limit of the ratio as change in time approaches 0. So we see these four angular quantities are analogous to these four rotational quantities or linear quantities. Now, we want to find out if there's a relationship between the translational or linear quantities and angular quantities. So is there a relationship between angular and linear quantities? So let's examine the following rotating object that's rotating in the counterclockwise positive direction. So this is our axis of rotation. This is the point that we choose. And let's suppose the distance from the axis of rotation of the point is given by uppercase R. So this is our radius of our circle, circumscribed by this point as the point moves about the axis. Now let's suppose this point moves a very, very tiny amount. In fact, it moves an infinitely small amount given by dl. Now that means the angle created by this displacement, by this rotation, is given by d theta. Now recall the relationship between the angle theta, the radius r, and this distance l. It's given by theta is equal to L divided by R. So that means we get the following formula. D theta is equal to DL divided by R. We can bring the R to the left side and we get the following result. DL is equal to D theta multiplied by R. Now we're going to use this in just a moment. So, we want to somehow build a relationship between instantaneous velocity and angular velocity. So instantaneous velocity is given by our dx divided by dt. And because this distance is infinitely small, that means dx is equal to dl. So velocity is equal to dl divided by dt. And we just said dl is equal to d theta multiplied by r from this relationship. So that means we can substitute this quantity into dl and we get velocity is equal to d theta multiplied by r divided by dt. Now notice d theta divided by dt is simply our angular or instantaneous angular velocity. So we can simply plug in our omega, our angular velocity, into this entire quantity and we get the following relationship, the following equation. So instantaneous velocity of this point is equal to the instantaneous angular velocity multiplied by the r. So that means as the point moves further and further away from the axis of rotation, the velocity, the instantaneous velocity at that point will increase. If it moves closer, it will decrease. Now notice that the omega remains constant. So at any given point, the omega will be exactly the same. The instantaneous angular velocity will remain the same. Now, let's try to build a relationship between our alpha, our instantaneous angular acceleration, and our instantaneous angular or tangential acceleration. And we also want to build a relationship between the radial or centripetal acceleration and this angular acceleration. So let's begin with the translational or with the tangential acceleration. So recall that tangential acceleration is equal to the derivative of the instantaneous velocity function with respect to time. Now we just said that velocity is equal to omega, our angular velocity, times our radius r. So we can simply plug this quantity into this v and we get the following result. So this is a constant, so we can take that out. So we see that d omega divided by dt times r is equal to a tangential. And d dot or d omega divided by dt is simply our alpha, our instantaneous angular acceleration. So we can take this and plug it into this and we get the tangential acceleration is equal to our angular acceleration times r. So once again, as we move further away from the axis of rotation, we see that our tangential acceleration increases. Now what about our radial or centripetal acceleration? Now we know that this equation or this value is equal to v squared, our instantaneous velocity squared, divided by our radius r. Now once again, we take this quantity, we plug it into this, we square, and we get that our radial or centripetal acceleration is equal to omega squared or angular velocity squared multiplied by r.